Okay. Hey, a couple mini updates. I got an email from a college student at Paradise Valley Community College, and you'll hear more about it during some of the announcements. He was one of two scholarship winners that we paid for, sponsored. The Sam and Sana PAS student scholarship that we award every year was upped to two recipients because we sold some of our donated telescopes. We're sitting there looking at all these donated telescopes, trying to figure out what to do about them. And we have an inventory of 5 telescopes that we loan out. And so we decided to go ahead and sell them to members at 50% of cloudy night prices. In other words, if there was a Dob, an 8-inch Dob on sale used on cloudy nights for $600, we sold ours for $3 at half price to members. And doing that, we ended up raising enough money for a second $1,000 scholarship, which was kind of cool.
Nice.
So, another reason to be a proud member of PAS. I have some info for some of you. This is for members only. We have, over the summer, come up with, of course, all of you know, a new logo for PAS, and you can see it on the left-hand side. And I can show you, this is what our name tags look like. I don't know if you can see that too well, but anyway, and the logo is on the name tag. And so these are both available. The logo patch is a sew-on patch. It's got an adhesive sticker on the back. And when we sell you this logo, we remind you that sticky is just to keep the patch in position while the seamstress is sewing it. Some people say, does that mean it's an iron-on patch? No, it's a sew-on patch. But anyway, we have now for you available as many as you want to buy of the patches for your headgear and etc. and your over jackets. It's a nice way for you to let people know about your hobby. And of course, the name tags are available, name badges are available. If you're interested in getting yourself a couple patches, contact me and I'll send you the link where you have to go on our website to make the purchase. Anyway, anybody have any questions on that one? Hearing none. Stewie's moving on. Okay, this is our business card that we have created. And as you can see, it kind of condenses the mission of this organization as we reach out to our community to educate them about our exploration process, the fun hobby that we have of the cosmos. And I thought I'd let you know, we give these business cards to members to have them carry around with them so that if they run into somebody who says, hey, what do you do for fun? And they can say, well, I'm a line dancer, I'm an astronomer, Parse, and here's a card of the club I belong to. So anytime we get together at our star parties and our lecture series, just ask me. They will be available to you at all of our events for members to have in their pocket. I mentioned to you that we have a loaner telescope program going on, and these telescopes are in my garage. And we've got Dobsonian. We've got a solar. We have sea stars. Actually, we have 2 sea stars. One that we bought, and then another one that was donated to us by Star Arizona down in Tucson. What an organization. A bunch of us went down to Star Arizona to have scopes repaired. And what ended up happening was we told them about our loaner program, and they were impressed. And they said, Stu, take this with you. It was a return. Somebody bought it from them and then returned it for whatever reason. And then they gave it to us, and we brought it, and now it's in our loaner inventory. So proud of what this organization is doing to help our members. This program allows you, as the slide is trying to tell you, it allows you as a member, if you don't own a telescope and you're thinking about it, or you want to change your style and get a different one, we've got a solar telescope, 2 sea stars, we've got a Dobsonian telescope. So let us know.
Yes.
contact telescope at pasaz.org. And the loan time is a month. And if the telescope you have has no one waiting in line behind you, you can have it for a second month. So you can really get your hands wet, if you will, on playing with these telescopes and using them and developing and improving your skills. So, any questions on that one, guys? And by the way, it's free. See that where it says free up in the upper right-hand corner. Okay, take a look. Since 1948, over at Phoenix College, this organization got its start, and we continue to this day. And the question is, well, if you are first time joining us on this Zoom lecture, you too can join by visiting us at pasaz.org. We have a link for you where you can join. And I have more information about this process. But to our members, a couple of years ago, when I first took over as the president, we had 70 members. We're now up to 154 members.
Wow.
So I'm telling you, the word is getting out that the leadership crew on this organization and the events that we've been able to put together for you and our lecture series, I think are attracting more people to get what they want out of their hobby known as astronomy. Okay. Speaking of membership, take a look at this. I'm going to be quiet for a second and just let you digest what's in front of you while I wet my whistle. Okay. So, membership. As the slide in front of you says, our membership normally runs January 1 to December 31. And if you join after July 1st, then of course you can join for half the fee that you see. The annual fee for individuals is $30. And the student membership is half that price, as you see on the bottom, but it requires a student ID. There is a family membership for 35. And I just thought it would be a good idea to alert our members now, and we will be sending this slide out to the members within the next week, that it's renewal time. And we give you a 1 month grace period in January to renew. And if you do not renew, then we take you off of our mailing list. And the question comes up, why would I want to join this organization? Well, I just mentioned to you the 2 scholarship programs. We have events where we have telescope operators in our Star Tours program that you'll see in a minute. And we purchase materials for them to distribute, whether we're going to elementary schools, Cub Scout events, corporate events. The Star Tours group gets paid for their work, but we use your membership to pay for a couple things. Number one, we have insurance to occupy quote unquote Phoenix College classrooms. The college requires us to have insurance. And then when we go out to events, we're required to have insurance. And our members are insured when they go to the Star Tour parties, etc. So your membership fee pays for materials. Oh, by the way, we have our website internet link. We have to pay for some of that. So it's not a lot of money compared to other organizations that you might belong to. We're right in the same ballpark with other astronomy clubs across the nation. And I thought it would be a good idea to remind everybody now that your membership is about to expire come the end of next month. And I know we're just starting here on the 7th of November, but put that on your calendar so you can take care of that. And here's the key issue. To renew, you want to go, excuse me, I did it again, didn't I? You want to go to our regular page at www.pasaz.org, And on the left-hand column, there is a link called Join Our Society, and that's where you can sign up. So, any questions from anybody? Hearing none?
Yes, Stu, Stu, there was a lifetime membership too, wasn't there?
Yes, and it is $500 for a lifetime membership. I thought I put it on this slide, and somehow or other it didn't show up. And then for over 65, the lifetime membership is $250.
Okay.
So thank you for that question, and thank you for the reminder. Okay, Stu shall move forward. You heard me mention that, the Star Tours group. This is a group of members who have their own telescope. They are part of a team. They have a uniform. They have this shirt with patch. They have this name tag. They have this patch on a hat. They're required to represent you and me professionally when they go out. So this Star Tours team are made up of individuals with telescopes, one, who know how to operate their telescopes and who know how to articulate and explain to members of the public, whether it's brownies and Boy Scouts and Cub Scouts, or college students, or a corporate convention. We are hired for all of these events, and the Star Tour team members go to these events and perform. We did Arco Sante a couple of weeks ago. What a wonderful event that was, and got a good write-up in a major publication because of that. But the point is, your organization is represented by your PAS Star Tours team. If you have a telescope, if you know your night sky, and if you want to earn a couple bucks sharing your knowledge, then you have a job. And your job is to contact on the internet, email startours@pasaz.org. Questions? Hearing none. Okay. By the way, this interesting program, it's kind of fun. When we go out to some of these events, it's amazing what happens. Sometimes, Don, you and I were downtown, right in the middle of Phoenix, set up a telescope, and we had buildings all around us, and the only target we could zoom in on was the moon. People got in line a second time and a third time just to see the moon because they'd never seen the moon before. The Arizona Science Museum had invited us down there. Wasn't that right, Don?
Right, that's it.
And so we were down there with our scopes, and it was so cool because you had adults and children saying, wow, I didn't know what are those things? And they're impact craters. And this, because they normally see a big white saucer, as we all know. And so the fun part of it, besides, showing off your telescope and sharing what you know, and you get paid, is to see the eyes and the smiles on the people when they get to see something. Okay. Every month, there's something different in the night sky, and we're getting into the winter months, and the Orion Nebula is visible, of course, and there are other objects in the night sky. As you can see on the bottom, I get this information from spacetourismguide.com. I would recommend, if you have a camera handy, you might want to take a picture of this slide off of your screen to use this for your key dates, number one. And number two, use that link that's on the bottom, spacetourismguide.com. Awesome information there. By the way, we have some amazing links on our website that you might want to pursue when you visit pasaz.org. I'll leave this up for you a little bit longer. Does anybody have any questions about these events? Of course, these are in the Northern Hemisphere. I have to clarify. One meeting, somebody got in touch with me and said, "Hey, Stu, you realize that those are only in the Northern Hemisphere?" And I said, "I do." And they said, "Well, Stu, you should tell people that." I said, "Okay." All right. Northern Hemisphere, everybody. Anyway, spacetourismguide.com. Excellent place to get additional information, but here are the items that might interest you during the month of November for your pleasurable viewing. Okay, moving on. This is what I was talking about a little bit earlier. I just got a second email from an email from the second student at the college thanking us for her $1,000 scholarship. I'm telling you, I was at PVCC last month, new president on campus. I mentioned this at our last meeting, and I told her about our program, that we appreciate being able to use the classroom for our lecture series when they're held there and for our telescope workshops. And I said, oh, by the way, we give out a $1,000 scholarship this year. We're giving out two. She was just so elated and happy. And so we have now gotten an email from each of the recipients who have expressed their appreciation for their scholarship. I will be announcing to all of you through the newsletter and an email a copy of their appreciation email. One, we'll put it in our newsletter. Two, and we are going to invite them to our next meeting, and hopefully that will be in December. So it is just so, I mean, it feels good to see the look on their face. Last year when we had our student come to a meeting at campus, Don, you remember that?
I don't think I was there.
Yeah, and he was just so appreciative, so articulate. He says, I wasn't sure if I was going to stay in astronomy, but now you guys have encouraged me to pursue it. I said, oh, good, good. So yeah, there you go. The interesting thing is that we, meaning your leadership team, we gave them our criteria of what we wanted the money to go to, meaning who we wanted the money to go to. We sent them a check for $2,000, and we have a contact, a good working relationship with the community college. They do all the work. They announce the availability of the scholarship, the criteria. They review the applicants. They interview the applicants. They choose the applicants, and they turn around and tell us who was the winner. I mean, it's one of those the yin and the yang of a great relationship to accomplish something good. So I can't say enough good about this particular project that PAS is involved with. What say you? You guys like this idea?
Yeah, I remember a couple of years ago when we had to do all the work. We did all the interviewing and everything. That's great that they're willing to do that for us now.
Well, and they're right there with the students,
Right.
so it's a lot easier. So another camera shot for you people. If you have your cell phone, take a click of this again. This is a different link for spacetourism.com. It's stargazing-arizona/. This particular link gives you, I think it's 12 or 18 different places to go to here in Arizona. A lot of you guys who are up in Wisconsin, I know you like your dark skies and whatnot, but the word around the country is Arizona really does have a good dark sky situation, with the exception of course, our two metropolitan areas, Tucson and Phoenix. And so the Grand Canyon, a Bortle 1, if you will, I'm guessing. Who has been to the, Mike, have you been to the North Rim on the canyon? And is that an accurate number, Bortle 1 on the North Canyon?
Are you talking to me?
Yeah.
Okay. Portal 1 or Portal 2, it's very low. It's among the lowest in the nation.
I know, but is it, what, am I right that that's the Bortle reading up at the North Rim of the canyon?
Yes, Portal 1 or Portal 2. It's
There we
very
go.
low.
So besides the Grand Canyon, the link that's in front of you, take a picture of that link with your cell phone. That is the site you want to go to check out, and they will tell you about where our speaker, Dr. Al Conrad, comes from with the large binocular telescope. They will tell you about that and other places to go to. So let me see. Now I don't see Richard. Are you with us, Richard Sauerbrunn? I don't. Let's see.
He's signed in, but doesn't seem to be active.
There I am.
Oh, okay.
I'm here.
Oh,
Stu,
okay.
remember, Zoom only shows you a small
Yeah.
portion of the people that are here.
Yeah.
You have to set your screen up. There's 20 folks online tonight.
Okay. And I'm looking to see if our speaker has arrived. I do not see his sign in yet. We told him he could join us early or at 7:30. So I've got about another 7-8 minutes to go. Let's do this. I'm going to leave this up just a little bit longer. I'm telling you, you want to take this link and use it. And my also other recommendation, people, is you want to show some of these links like this one to your family, because they make for a nice outing. You know, you're not always going out with your telescope. You're going out with your family to visit an observatory or a science lab, if you will. For instance, meteorites. Meteorites are on show and available for you to see at ASU. I mean, if you've never seen a meteorite, I've got a gavel here that was given to us with a meteorite on the end of it. But ASU has one of the largest meteorite collections west of the Mississippi, if not the largest. And so not always are you going out with a telescope. You can go out and visit locations like the meteorite inventory at ASU. And I would strongly recommend you take a look at this link, share it with your family. Okay. So I'm going to leave this up here for a second and move this over here. I'm going to give you a little bit more background about the location. 2 hours northeast of Tucson, Mount Graham. And as was mentioned, a couple of you who've been there, once you get there, they'll put you on a bus and take you to the top, but it's a bit of a ride as well. And a couple of things that I did some research on this location. They call it the Large Binocular Telescope, the LBT. They have two 8.4 meter mirrors. That's their diameter. These things are big. And you're on the top of a hill. Like Chile, you want to be as high in the atmosphere as you can for multiple reasons. A better view. Well, here they are at 3,200 meters. So they're way up there. And then they are the home of course, the Vatican Telescope. And as I mentioned, they have the moth problem. And Mike mentioned they have to clean those mirrors, and they don't have to take them down. They actually have a piece of equipment that moves up to the mirrors themselves and cleans the mirrors. When he described it, and I watched a video about it, reminds me of they now have these machines that do the high-rise windows on the outside. They're just machines, no more people anymore. They just have these machines that wash them. The same. And my understanding is the year was 2005 when the Large Binocular Telescope was first built. But just the construction of it was amazing. And our speaker, Dr. Al Conrad, is going to be telling us about a new development in optics. And I want to share something that Richard, maybe you can give us a little bit of a highlight as well as we wait for Dr. Conrad. We have a new optical approach to stargazing, especially for our Star Tour events. And this process means that people, when they come to the telescope, they don't put their eye up to the telescope, they stand back and look at a TV screen. Richard, are you still with me?
I'm here. Yeah, I'm here.
So why don't you, while we're waiting for Dr. Conrad to explain that different optical approach to sky watching?
Okay. Interestingly enough, this coming Sunday night, Stu and I are doing an event in South Phoenix that is sponsored by the Phoenix chapter of the what is it? The something sighted impairment foundation. It has to do with individuals that are partially impaired, not totally blind, but certainly unable to see normally. And they asked us if we could present the new technology that is becoming very popular over the last few years that enables people that are challenged with their vision to be able to see these astronomical objects. And basically, we simply attach a high resolution camera to the telescope in place of an eyepiece. The camera is significantly more sensitive than the human eye and can gather more photons, gather more light, and see objects which are completely invisible to the human eye, even in a low light polluted situation. But in a place like Phoenix, if you've been here and looked up at the sky, even on a clear night, you know you can only see a dozen stars at best. And you cannot see any of these objects that these cameras can see. So we attach the camera to a television screen or a large computer monitor, and that allows people to see objects that they couldn't see through the eyepiece.
So as Richard's explained it, what is really wonderful about this approach is he has the equipment for that type of a setup. Mark Johnson, our vice president, has the same type of equipment for that setup. And so when we go to events, we can accommodate not 20 or 30 people in line to look through your eyepiece. You've got 100 people who are in an audience, or 50 people in an audience who can watch what real time what you're seeing with your telescope on that monitor or that TV screen. Just it's I think a time saving, and it blows up the image. All of us know when you have a newbie come up to your telescope and they look in the eyepiece and they say, "I don't see anything." And you say, "Well, give it some time." No, we say, "Well, that can't be." But anyway, yeah. So I love this approach. For that event Sunday night, we have from NASA, I'm trying to sound like a European, from NASA, some sky imaging. You ready for this? In Braille. That we are going to show these people that is available out of NASA. It is, what everybody understands Braille. It's 4 rows of dots that go up and down, and the different configuration are everything from letters to numbers. Anyway, so we'll be taking that to the event. I see that Dr. Conrad has in fact joined us. And Dr. Conrad, I had the information about the internationally famous large binocular telescope, LBT, and I would like, if it's okay with you, to have you take over the floor. But before we do that, I want to remind everybody that please, as I will do when I shut up, is to please turn off your microphones and your cameras, because they have a tendency to be a distraction, especially when someone comes into your room and tells you the dog needs to be fed, or somebody's at the front door, and therefore we're interrupting our speaker. So at this time, I'm asking everybody to take care of that for us. Turn off your camera, turn off your microphone, and I am going to introduce Dr. Al Conrad, University of Arizona, the Large Binocular Telescope. He's going to be talking to us about some new optics. Dr. Conrad, the floor is yours.
Okay, great. I'm just going to share my screen here and put up these slides, which I've prepared, and get going. Can you see the slides okay?
Yes, sir.
Okay, great. So today I'm going to be telling you about our observations of EO with the Shark Viz instrument at LBT, and how that will be ushering in a new era of planetary imaging that we couldn't do before. So these are the topics I'll cover today. Probably all of you are familiar with Jupiter's volcanic moon Io, but I'll give a little brief overview of Io and the volcanoes that we all know are active there on that moon of Jupiter. Then I'll give some background about the LBT. Again, I think probably most people have at least heard of it, but I'll just give a slide or two about LBT. And then I'll talk about adaptive optics. That's another technology that I'm sure all or most of you are aware of, but I'll talk about some changes in the technology that have empowered this new mode of observing. And then I'll talk about the SharkViz instrument itself. And then I'll get to the meat of the talk, which is our observations of Io using the SharkViz instrument. And then I'll spend about the last 5 minutes talking about future plans, both for SharkViz and for a new, even higher capability instrument that we're planning to bring to the LBT. So Io is the innermost of the 4, Galilean satellites that were famously discovered by Galileo when he first turned his telescope to the heavens. It's roughly the size of the moon, a little bit larger, and volcanic activity was discovered famously in 1979. Probably some of us are old enough to remember that, and I certainly do. I think a lot of us maybe even remember where we were, because it was just such a fantastic image when this plume rising hundreds of kilometers above the surface of Io, or at least tens of kilometers above the surface of Io, came back from the Voyager imaging. And now coming, fast forwarding to the future, to the current day, we have the Juno spacecraft is just finishing up its study of Jupiter and its moons, and most recently Io. And by that count, we're up to around 340 active volcanoes and hotspots on the surface of Io. So what powers these volcanoes? Well, it's heat, of course, and the heat is generated by what's called tidal heating. So again, probably a lot of this is review for many of you, but Io is, as are the other Galilean satellites, tidally locked, meaning they have, like our moon with Earth, there's one side always facing Jupiter. So you have the anti-Jovian point and the sub-Jovian point. The sub-Jovian point refers to the point on Io that is always facing Jupiter, and that's also the 0 point for longitude. So everything is measured east and west of that point on Io that's always facing Jupiter. And these moons, the 3 innermost, are in resonant orbits, meaning that every time Io goes around twice, Europa goes around once. And every time Io goes around 4 times, Ganymede goes around once. So there are common cases where these moons line up. So the same tidal forces, like cause the rise and fall of the ocean tides on Earth, which are stronger when the moon and when Earth lines up with the moon and the sun, it's similar that when Io is caught in like a tug of war between Jupiter and Europa, that there's these tidal forces, but they're much stronger. They're stronger to the point that they actually distort the crust and mantle of Io, and that results in a lot of heat. And that heat is then dissipated and transported somehow below the surface of Io to these volcanoes. But that mechanism is still an open question. And that's one of the many interesting scientific open questions that EO presents us with. There's three leading theories for how the heat is transferred below the surface of EO. Two of them assume sort of a, I'm sorry, yeah, two of them assume sort of a shallow heating mechanism, either in the asthenosphere, which is this thin layer right below the surface, or an entire magma ocean right below the surface, or then there's a competing theory that it might be happening deep inside of EO, deep in the mantle. And a publication produced by one of our co-authors, Ashley Davies at JPL, shows that there's a slight preference towards the shallower methods, based largely on a lot of this data coming out of the Juno mission. So to understand processes on EO and answer some of these open scientific questions, it's important to just be regularly monitoring what's going on all these hotspots. And so that's typically been done from spacecraft. And there's been three main missions, sort of separated by a few decades from one another. The original Voyager discovery of volcanic activity in the late 70s. That was just during a flyby. And then Galileo, which stayed in the area for quite some time, orbiting Jupiter, and acquired quite a lot of data. And then more recently, Juno, which started its mission in 2016 and has just finished at least studying EO in the early part of this year. And then in the gaps in between, the Hubble Space Telescope has been sort of the go-to Earth-based telescope for taking visible light images of EO, but at much lower resolution than these spacecraft, which are close by. So here's two images of EO. One of them was taken from space by the Hubble Space Telescope. The other one was taken from the ground. And but which is which here? And I think the answer might surprise you. It's actually the sharper image on the right that was taken from LBT, and the one on the left is a typical highest resolution image that was taken with the Hubble Space Telescope. And as we'll get into later, the basic reason is because the Hubble Space Telescope is a wonderful facility, but its mirror, roughly 2.5 meters, is much smaller than the mirrors on large telescopes on the ground. The difference, of course, has been that it's in space above the Earth's atmosphere, and so it's not subject to the blurring effects of the atmosphere. Whereas telescopes on the ground have to contend with the aberrations that are caused by the blurring effects of the atmosphere. However, thanks to adaptive optics, and as can be seen dramatically in this image, we can now take advantage of the larger mirrors to see more detail on the surface, from telescopes on the surface of the Earth, thanks to adaptive optics. So just step back and talk a little bit about the Large Binocular Telescope itself. As the name implies, it's got two mirrors. Here's a nice picture of it and enclosure. It's a square dome. It's a little different than most domes you're used to that are more spherical. These two large shutter doors slide left and right. And I was just up there last month for the company picnic, and and they put on a real show at sunset with opening these doors, and it's an incredible facility. Just the pure size of it is amazing. It's located on Mount Graham, also known as Emerald Peak, in eastern Arizona at an altitude of a little over 10,000 feet, 3,200 meters. There's two mirrors on a single mount. So meaning that it's not two telescopes, it's a single telescope with two mirrors on a single mount. We always point to the same, both mirrors point to the same object. It's a single telescope. The collecting area, so just our ability to just go faint and see faint objects, is equivalent to roughly a single circular 12-meter telescope. But what's maybe more important for the science I'm interested in, which is more brighter objects, but looking at them at high angular resolution, is this roughly 23-meter so-called baseline, which is the edge to edge, the width of the mirror. You can't really call it a radius because it's not a circular mirror, but the width of this telescope is 23 meters. So a little bit about adaptive optics. Adaptive optics corrects the blurring effects of the Earth's atmosphere. So, the stars that, the blurring effect that we see in the twinkling of the stars, and the fact that without adaptive optics, you're limited basically by the seeing cells in the atmosphere, which on a good site are maybe 20 or 30 centimeters. It means that you really are not going to see more detail without adaptive optics with a huge telescope than you do with a 20 or 30 centimeter telescope. So, but enter adaptive optics, which compensates for this blurring effect by measuring the so-called wavefront, the light from these, celestial objects, and it comes from, great distances. In some cases, thousands and thousands of light years, millions of light years, and makes its way just to be in the last second or two of its trip, distorted. This perfectly flat wavefront is distorted by the atmosphere, and what we do is with a sensor, we measure that distortion rapidly, roughly like 1,000 times per second, and then we feed that information into a mirror that can be distorted, can be deformed through hundreds of actuators behind it, and it takes on the exact reciprocal shape of the wavefront coming in, and thereby this wavefront, which has been distorted and is wrinkled, if you will, hits this deformable mirror, which is the exact reciprocal shape, and what bounces off is a flat wavefront. And it's just like magic. It's like putting on a pair of spectacles. When you close the AO loop, you go from an image like this one on the left to one that's very sharp, like this one on the right. However, historically, adaptive optics has always had been set up so that the science channel is in the infrared. The wavelengths that are longer than the visible wavelengths that we see with our eye. And the reasons for that are, it gets a little bit technical, but it roughly, the shorter the wavelength, the harder things it gets to do correction. You're basically just dealing with the wavelength itself, the distance from the peak to peak in the wavefront, and the longer wavelengths are easier to correct, or the correction you get is going to be better at seen at longer wavelengths. And also, the wavefront sensors themselves are looking at optical light. So the trick has just always been to use a dichroic, which is an optical element which can preferentially, pass infrared light through while reflecting the visible end of the spectrum. And so that way you're not throwing away any of your science photons. And however, it's always sort of been like the holy grail is to get to where we can do adaptive optics at visible wavelengths. So with advances in adaptive optics, mostly deformable mirrors that have more actuators, and the detectors themselves, both in the science camera and the wavefront sensor. As you probably are all aware, it's amazing what's happening right now with these low noise, either electron multiplying CCDs or these CMOS devices that you can really, there's been a revolution in what's possible with these new visible light detectors. So here's an image of the secondary mirror of LBT. So LBT is unique in that its deformable mirror is the secondary mirror. All other telescopes, actually a few, one of the four VLT, Keck is now has a plan. It'll be about 2 years before they have theirs, and IRTF is getting one. But for a long time, LBT was the only telescope which had its the deformable mirror is actually the secondary mirror of the telescope, so that all instruments except the prime focus instruments are benefit from having an adaptive optics correction applied to the incoming beam. And so, as a result of it, this early decision, 10 years ago, the decision was 15 years ago, and the actual first light for LBT with an adaptive secondary was in just after 2010. So 14 years ago, this was realized, and part of that decision required building a secondary mirror with more actuators than you typically had on the smaller. This is the deformable mirror that has been in use in Keck for a long time. They'll be upgrading, but for a long time it's been, so there's fewer actuators, like roughly twice, half as many in most of the deformable mirrors of other 8 to 10 meter telescopes. So we already had the more actuators, which was needed just because of the pure size of it. We already had the more actuators, so-called extreme AO, when you get up above 500 or 600 actuators. Now, of course, there's deformable mirrors up to 2,000, but those are not adaptive secondaries. So we already had a large number of actuators. And then the second piece of the puzzle to get to being able to do adaptive optics in the visible was using one of these, in our case, Occam, electron multiplying, very low noise CCDs. Here are some of the numbers. There's a lot of numbers here, but the takeaways are much lower, less than an electron readout noise, while actually reading out more pixels faster. So that's revolutionized visible light detectors. So these two things combined, more actuators and visible light detector technology advances, led to the promise of putting a visible light science channel on the LBT. And it was basically all ready to go. It's called SharkViz, and it was developed by Fernando Pedicini, was the PI, and his colleagues there in Rome, in Italy. Italy is a partner in LBT, and it was pretty much ready to have their pre-ship review in late 2019, and then the pandemic hit, and so everything sort of shuttered up. And then around 2023, we got going again. And I was lucky enough to be the scientist that was responsible on the LBT end for working with the Italians to get this instrument commissioned onto the telescope. And then one of the first things we wanted to look at was EO. So just stepping back for a second, looking at the history of adaptive optics on telescopes, beginning with the first adaptive optics system on a large telescope, which was the 3.6 meter CFHT mirror called Pueo back in the late 90s. And then with Keck, VLT, and Gemini following quickly in the early 2000s, LBT deciding to use this adaptive secondary, it Took a little longer to get that technology working, came online with their adaptive optic systems. All of these operating in, I say at K, but they all operate at K band, and the other, J and H band, infrared atmospheric windows that you use when you observe in the infrared. But then in around 2010, another University of Arizona telescope, the Magellan telescope in Chile, was the first visible light scientific channel on a large telescope. The Magellans down there are 6.5 meters, and again with an adaptive secondary. In fact, it's a whole long story. The adaptive secondary they used was actually intended to go on the LBT, but was damaged in such a way that it couldn't be used on LBT, but was repurposed to work with Magellan. But so a large number of actuators, so they were able to do a visible light AO system. And around that time, the VLT commissioned the Sphere instrument, which has been doing tremendous work at visible wavelengths. And now LBT coming along a little later, we've commissioned in 2024, but because of the viewing geometry and other factors, we were the first ones that have turned our telescope towards EO to observe it using visible light adaptive optics. Okay, so about the observation, we observed it. It was one of the first objects observed during the latter part of commissioning. The instrument went on to the telescope in August-September timeframe, and we observed EO in November 3rd last year. I'm sorry, November 23rd. I remember it was the eve of Thanksgiving. And so we caught it, within a few weeks of opposition. We always try and observe EO when it's at opposition, and so fully illuminated and also at its closest. And then we observed it again on January 10th. But and we were able to read it very quickly, just 10 milliseconds per frame, so 100 frames per second, and observe for 10 seconds. So we took 1,000 in each of the 3 filters, VIR. And then we made a similar observation, but conditions were a little better. We were able to read out even faster on January 10th. Or the correction was a little better. The conditions were actually about the same. And so the total time on source was just 45 seconds for this observation. But being a new instrument and all the overheads of a large telescope and getting everything working, we were several hours on both of these nights acquiring this precious 45 seconds worth of data. And so in the raw images, we got pretty good correction. So we measure the correction of angular resolution in milli-arc seconds. A milli-arc second being 1,000th of an arc second, and an arc second being a 3600th of a degree. I think we're all aware that either the moon or the sun subtend about 1,800 arc seconds, half a degree. And so a single arc second is much smaller. The full disk of EO is about 1 arc second. And so 24 milli-arc seconds was pretty good. So we were able to get quite a few resolution elements across the disk. And it's the theoretical limit though would be more like 16 milli-arc seconds. And so we were able to resolve features on the surface of EO down to about 80 kilometers. And spacecraft imagery will, the Juno images, I just happen to be reviewing a Juno paper right now, and they're down around 10 or 5 kilometers per resolution element in most of their imaging. So 80 is still quite a bit more, but we're doing this from much further away here on Earth. And if we could achieve that 16 milli-arc second theoretical limit, that would take us down to about 50 kilometers on the surface of EO. So we noticed something right away in these images. Even these are pretty much unprocessed raw images. It's just, you know, adding together the 1,000 frames with some shift and add to register them. And right away we could see there was something unusual that for those of us who were, you know, looking at EO a lot, are you know, used to some of the dominant features. And there's this volcano down here called Pele that has a persistent red ring around it. And usually that whole ring is completely intact, but we could see that it looked like something here at about the, you know, near the 3 o'clock position, 2:30, 3 o'clock position, had like taken a bite out of Pele's ring. And when, so just stepping back for a second, a little bit more about this feature on EO. It's part of a persistent plume deposit coming out of Pele. So Pele is a larger volcano, more powerful volcano on Eo's surface, and it's constantly replenishing this ring, and we know that because it's red. If it suddenly stopped for some reason, which it never has, then it would change color. It would become more yellow, and so so we know it's constantly replenishing. And you know, this is a image here is a high resolution image of EO that is produced by the USGS, and it's made of a mosaic of in-close images taken by both Voyager and Galileo. They sort of just picked which ones they were best from each of those missions. There's a new one of these coming out, by the way, that will include the Juno visible light imagery. And so it'll be all three. And you know, it's normally this red ring is completely intact. This little volcano over here is called Pelon, and that's the one we'll be talking more about in the slides. It's a huge feature. It's 1,200 kilometers across, dominates the hemisphere. So when we you know, did some more careful processing of the images and combined the three different filters to make a color image, it became even more apparent that there was something had taken a bite out of Pele's persistent red ring. It seemed like this was somehow associated with Pelon, nearby Pelon Patera. So although, you know, Juno had been in orbit around Jupiter since 2016, it had never imaged this area. It was in this polar orbit around Jupiter, and so it got great images, rarely seen of the poles, in particular the North Pole of EO. But this feature is just south of the equator, and just as luck would have it, it had never seen this feature we had. So to find a visible light image of this area at high resolution, we had to go back 17 years to when New Horizons was on its way to Pluto Charon and flew by and took a snapshot, and you could see back then 17 years ago that Pele's red ring was intact. And so we knew that this feature was, you know, at least as recent as 17 years. And there's been similar events that have been observed on EO, but never before from an Earth-based telescope. And in particular, during the Galileo mission, same area, the Pele's red ring, same source, Pelon. There was a strong eruption, and from Pelon, and this dark volcanic material, plume deposit flowed out, covered the ring, but then with Pele persistently erupting and redepositing fresh volcanic material, it eventually pretty much erased all of the effects of this resurfacing of that area from Pele. So we know that these these events are temporary and or can be temporary. We don't know they all are, and we know that this one in particular took a few years for Pele to repair itself. So we set about to try and find out what eruption might have caused the resurfacing that we saw in our Shark Viz images. So my colleagues on the publication have access to other assets, and in particular Juno, not the visible camera on Juno, but the infrared imager on Juno. I said earlier that this area had not been imaged by Juno. I meant in the visible, with its visible light camera. Juno had both a visible and an infrared, with infrared being the main focus of the mission scientifically. And so we had access to those images through Ashley Davies, and I mean they're public, but he knew where they were and how to interpret them quickly. There was IRTF, Gemini North, Imke de Potter, and Catherine de Cleur, who were colleagues on the paper, have been observing EO with Keck for decades and had a lot of imaging. And so we looked through all these, going back a few years, and looking for any sort of sign of a strong eruption there in Pilon, and one jumped out. So these are in spectral radiance, this column over here, gigawatts per micron. And so you can see all the numbers are modest, tens or maybe 20 here and there. But then there's this large one here of over 500 gigawatts per micron spectral radiance. And so we're fairly confident that, and it roughly coincides to what I showed earlier of a 2 or 3 year lifespan. We do hope to monitor this area. We're going to observe it again next month, and which is the next opposition. The Jupiter oppositions, as you know, are roughly every 13 months, and so it's an opposition this year on December 7th. So and we fully expect to maybe see that Pele will have repaired itself a little bit since we observed it in November and January of last year. So just a quick word about further image processing. So when we first submitted the paper, we wanted to get it out there quickly because we knew Juno was going to be imaging EO. They did their last imaging with JunoCam, the visible light camera, in February. We knew they were going to be looking at it in early February. And it's one of our co-authors said, Ashley Davies, he said, it's much better to publish something where you say, we see something for the first time, than to say, yeah, we saw that too. And so we worked hard, and actually just a few weeks after that second observation, we worked on the publication a lot before the January observation. The January observation was similar, didn't really turn up anything new. So we were able to quickly get it submitted, and we submitted it in late January. And then sure enough, Juno flew by in early February, but as luck would have it, it didn't, it came really close, but the actual area right there by Pilon was not in their imaging data. After we had submitted the paper, and we considered waiting. So we had these colleagues at Georgia Tech and Georgia State who had worked closely with the colleagues in Rome on this new deconvolution method, so-called deconvolution. And so deconvolution is it's kind of a tricky technology. The idea of it is, okay, the atmosphere is going to convolve the image with its blurring effects. And so what you can do, and what you always do when you observe using adaptive optics, is you measure a point source, a star, a nice bright star in a similar part of the sky, a nearby part of the sky, and then you get what's called the point spread function, a PSF. which is going to show some distortion. The AO is great, but it doesn't remove all the distortion. And so now you have an image which tells you roughly how the atmosphere convolved with the perfect PSF that entered the atmosphere to have this residual distortion. And so then mathematically you can use that information to deconvolve and try and get back to that original image before it was distorted by the atmosphere. And it's a sophisticated mathematical process. It requires lots and lots of computer cycles, and it was going to take months to do this. This deconvolution has been around for decades, but these colleagues at Georgia Tech and some of the people at Rome have this new method. They call it Kraken, and it actually looks at the frame-to-frame differences in the science images and in your PSF measurement to get an even better estimate of the wavefront, and thereby do an even better reconstruction of the actual the real brightness distribution of the object. And so, for example, in our convolved, before applying Kraken, we got this great detail, but over here at Loki Patera, we were a little, wow, you don't see the island. That lava lake has a sort of famous island in the middle of it. And after deconvolution, that island in Loki Patera shows up. So these are even better images. So yeah, we got it published. It took a long time in the review process from late January until we finally got it reviewed and out June 4th. And it was a great accomplishment for us. And I just definitely want to give thanks to all the co-authors involved. These are the folks at Rome, Italy, these first three, and then Imka, Ashley, and Catherine were the brain trust behind the science. They've been observing EO for decades with Keck and other, and LBT. We've done previous LBT observations with their collaboration, and then all the others who helped out. And these are the guys, Stuart and Doug, who did the Kraken deconvolution. So what are our future plans? Well, as said earlier, we want to observe EO at every opposition. That's the idea. We're going to monitor it now. There's no spacecraft there. The next spacecraft arrivals will be JUICE from the Europeans and Europa Clipper. But that'll be the early 30s. So for 6 or 7 years, it's us and other ground-based telescopes as they catch up and put their visible light cameras behind extreme AO systems. We also will observe asteroids, and we're hoping to observe Minerva actually next month, weather permitting. And also, there's these mysterious dark spots in Neptune's atmosphere that come and go, and we could explore those. They're visible in visible light, actually at the sort of shorter end of the visible light spectrum, 450 nanometers. And we could look at the rings of Uranus. And so there's a lot more in and of course, we're not mentioning here all the stellar and extragalactic science that is possible. But yeah, for our solar system, these are some of our plans for the near future. But what's the next big step for high resolution imaging at visible wavelengths at LBT? Could we do better? Could we even go beyond with this telescope? Is there some way we could even improve on the high angular resolution that we got with SharkViz, which uses just one side of the LBT? I probably should have mentioned that earlier. It's just using one of the two 8.4 meter mirrors, which means we can observe the same object, and we do. So during all those EO observations, we also observed it in the infrared with a sister instrument on the left side of LBT called SharkNear. But as far as angular resolution goes, we're using an 8 meter telescope is limiting our angular resolution. So to answer the question, let's step back to another observation that I was involved in back in 2013 and published in 2015. And in this observation, we were observing at longer wavelengths. And so recall, I said earlier that it's a lot easier to do adaptive optics at the longer wavelengths. So we were out there in the what's still called the near infrared, but the longer regime of the near infrared out. Near infrared is usually thought of as being 1 to 5 microns. And there's an atmospheric window called M band at 4.8 microns, and that's the sweet spot for observing EO from the ground as far as actually getting thermal information. So all those Keck observations and other telescope observations I referred to, they're observing out there at roughly 5 microns and seeing the actual heat, the thermal information. And but when we did it, we didn't just use a single 8-meter mirror like the other telescopes, Gemini, Keck, and others. We used the 2 8-meter mirrors co-phased, so that they're really acting as a single telescope. And in that way, we were able to use the full 23-meter resolution. And that was thanks to an instrument called LBTI, which is the one instrument at LBT currently, there'll probably be a second one coming, but that actually combines the light from the 2 telescopes into a single image. So it was observed for 1 hour in 2013 on Christmas Eve. And it again, we observed a PSF star. And if you look carefully, you can see down here, not Loki, this is Loki that's super bright here. But that's the data on Loki is what we published. But you can see down here, there's some fainter, smaller volcanoes that are not resolved. And you see here the fringe pattern that you get from the 23-meter baseline. So basically, perpendicular to these fringes, you're getting the resolution, which is the size of this central fringe. Whereas in the other dimension, you're getting the 8.4 meter resolution. So, but if you observe it for when it's close to transiting, and it's at a high enough declination. In this case, it was I think a declination of around 25. I'm just guessing, but it was it's close enough to the latitude of LBT that it transited fairly near zenith, and so you have a rotation that you can. The sky rotation becomes your friend. You don't try and derotate it, and this thing called the parallactic angle, you're probably familiar with it, dealing with Altaz telescopes, that we actually got almost 60 degrees of rotation. So you can see that the fringes at the beginning of our observation were in this direction, but by the end of the observation, they had rotated 60 degrees. And so in a way, you can think of this as you're sort of filling in to become a full 23-meter round telescope that can produce round images that are at this 23-meter resolution. You use the sky rotation to fill it in. So we got the highest resolution by far of M-band imaging by a factor of 3 from that observation, and we were able to combine those 7 images to a single image that would be equivalent to what you would take with a 23-meter circular telescope. And so in that way, we were sort of, that observation sort of marked us as having the capability of what is anticipated for the ELT. And just to remind you, there's these 3 extremely large telescopes coming. One is the largest, which is the 39-meter European ELT. And then there's the 30-meter telescope, whose future is unknown, that was supposed to be commissioned in Hawaii. And then the 26-meter, so that's really getting to be not that much bigger than our 23-meter LBT. The 26-meter is the Giant Magellan telescope, which is all the mirrors have been cast and is under construction in Chile. But all 3 of those telescopes are far away in time. And so in the meantime, LBT in this 23-meter telescope mode is the first, in many ways, it can be thought as the first of these ELT. Well, could we do the same thing that we did 10 years ago with EO, observing it at this higher angular resolution that is enabled by taking advantage of the 23-meter baseline? So, and what would that do for us? Well, the angular resolution, and one measure of that is the diffraction limit of the telescope. So that's like the best you can do. Is determined by the wavelength in the numerator and the size of the telescope, the D diameter in the denominator. So when you increase, so we do better when we decrease lambda. And so that's what we've shown, that with SharkViz, we now have these much higher resolution images of EO. We're seeing different things. We're seeing the cooler features, not the actual heat from the volcanoes, but we see them at much higher resolution than the infrared images, at 5 microns, and we're observing them at half a micron. So we're seeing 10 times better resolution. And then by increasing this D from 8 to 23, we roughly triple the resolution. And so instead of being what we're getting now with SharkViz, 16 to 24 milliarc second resolution, and I'll remind you that corresponds to 50 to 80 kilometer resolution on the surface of EO, we can do 3 times better. Here I'm conservative. I think we can actually go down to 5 milliarc seconds. So that would be, instead of the 50 that we're getting at 16, it would be like a third of that. So we're saying that this facility, this instrument that we're designing to take advantage of this 23-meter baseline, will get us down to at least 20 or less kilometer resolution. And recall, I said the Juno data is in the 5 or 10 milliarc second, 5 or 10 kilometer resolution regime. So we'll be getting even much closer to what's possible with spacecraft, but from here on the ground in Arizona. And so, I did a quick simulation of what we might see. I basically just took our real data. So this is on the left is one of the real images, the I-band image that we took of EO. And then I took the spacecraft image I showed, which was a much higher resolution, and I convolved that with roughly the resolution. I used 27 milliarc seconds instead of 24. I played with it until it looked roughly the same. So just kind of verifying that the simulation works. So I can make an image that looks about like our image by taking a much higher resolution spacecraft image and convolving it with the what's called the Airy pattern, which is Airy is the name of a mathematician, and it's just the shape of the image that you get through an optical system. And so then to see how we might do with this new instrument, which is being called the LBT Interferometer Visible Extension, I simply reduced the size of that Airy pattern, so it was a crude simulation in that way, by a factor of 3, and you can start to see, wow, you're really getting just tremendous detail. You can start to see, a lot of structure here and some of these, larger features, which are just blurred even in our current imaging, which is the highest resolution imaging from an Earth-based telescope to date. So that's what we hope to do with the live instrument. And when we do, coming back to this map I showed earlier, we had this population of telescopes that were in the 90s and the first decade of this century that were observing at K-band on 8 to 10 meter telescopes. And then we got the visible, was a big improvement in the angular resolution. And now with the first of the ELT observing at visible wavelengths, we'll go down to more like certainly less than 10, maybe even 5 milliarc second resolution. And the thing about this population here is none of these other telescopes will join it. This will have to wait for the ELT because you have to have this larger mirror and effectively 23-meter mirror in the case of LBT. So that's what I wanted to tell you about today. In conclusion, there's a new instrument on LBT. We use it to observe the EO and get the highest resolution images of EO ever acquired from a ground-based telescope. Those images revealed a plume deposit that was taking a bite out of the Pele's red ring. And this instrumentation and this publication ushers in a new era of planetary imaging from the ground at higher resolution. And then we have plans for a project called LIVE that would, by another factor of 3, improve the resolution of how we might observe EO and other objects in visible wavelengths with LBT. And with that, I'll stop sharing and take any questions you might have.
Thank you very much, Professor. Much
welcome.
appreciated. Much appreciated. I'm watching this and I'm saying, okay, I have a Schmidt-Cassegrain SE8, and I would love to have the deformable mirror to improve my angular resolution when I use visible light to look at the targets that I want to see. But I guess I won't. And as you described it so well with your visuals, I was thinking of a mattress with all those springs that we used to see underneath them, and they would go up and down. And you're saying that this mirror has these adjusters underneath it that changes just a silly little bit to adjust and improve the angular resolution, which leads me to ask the question, the thickness of the mirrors on this, do you know what it is?
I should know this. It's in the small number of microns.
Well,
Yeah, it's even though it's a 0.9, yeah, I should know this. It's called the thin shell. Thin.
Well, see,
And it's yeah, I should know it, but it's very small compared to the 0.9 meter width.
well, see, and the reason I asked this question, all of us are saying, okay, my wife's got this vanity mirror in the bathroom, and it's a pretty solid piece of glass, and I just can't see it putting a whole bunch of things behind it and changing the angular resolution on that thin piece of glass. But your mirrors are so thin that they actually are, quote unquote, can I use the word somewhat pliable?
Yeah, no, they're deformable. They're that's the name, deformable mirror. And the even the primary mirror, the 8.4 meter mirror, is also bent by actuators, but at a much lower frequency, like I think it's twice a second or something, to constantly, and that's true of all large telescopes. That's in fact, that's what the Palomar mirror, the 200-inch, was the largest telescope for a long time, right? It was in the late 30s, and it wasn't until the early 90s that Gemini VLT and LBT and others came along, and it was the breakthrough was that you could make the Palomar mirror is unbelievably thick, but these other mirrors are this thin meniscus or different names for it, and they have computerized. The thing that made the breakthrough was computers. It was the 70s that when computers came around and allowed for rapidly adjusting actuators, and so that's called active optics. So it's a similar word. There's adaptive optics, which is where you go to 1,000 hertz and you actually try to correct the blurring effects of the atmosphere. There's active optics, and that's where you just correct the effects of gravity, tipping the telescope up and down, and thermal, the temperature. And so this idea of bending glass to improve telescope optics is been around for a while, and yeah, you really do bend the glass.
I got a question for you from Mike, and it says, can deformable mirrors be done with acoustic deformations of ultra thin or mylar mirrors? Saves actuators.
Wow, that's an interesting idea. I don't know of anybody using acoustics to do that. I do know that the technology is evolving. You know, I hate to say it, but I'm Googling width of LBT secondary. I'm hoping they'll pop up because I wish I knew that answer, but probably somebody else could Google it. But yeah, it's 1.6 millimeters thick. So yeah, so I was wrong. So it's more than 1,000 microns, but yeah, it's still in millimeters. So it's 1.6 millimeters thick by 0.9 meters. 0.9 meters, you know, in width, in diameter. So yeah, the LBT secondaries and the other secondaries to date, like the one at VLT, actually, another surprising fact about them is that that thin shell is not actually attached in any way mechanically to the supporting structure, the reference body. It's held by magnets. So there's actually an air gap, and it's just floating up there. You know, you might think, oh my gosh, you know, what if the magnet somehow failed? This thing would just fall onto the primary mirror, but that doesn't happen. And so the mirror is deforming. But now that is sort of going out of favor. So there's a second new technology being developed by a company called TNO. I remember because it's the same initials as Trans-Neptunian Object, but that's not what this is. TNO, and they have what they think is a better idea. And in their design, the mirror, it is actually mechanically makes contact with the actuators. But the LBT mirror, so the technology. I'm sorry, I'm not really answering your question, but I guess I'm saying that people are looking at new and different techniques for building deformable mirrors.
Does anybody else have some questions? Jump in.
So, Dr. Conrad, in our astrophotography, there's been some incredible advances in deconvolution techniques using artificial intelligence. Do you see a role for AI as a means of further enhancing images?
Well, that's a good question. I don't know of specific examples. I know machine learning, which is a particular aspect of AI, gets used a lot, but the Kraken code that I referred to, I don't believe makes use of AI. But yeah, I'd be interested in that if you want to. Stuart has my email and stuff. Yeah, I'd be interested if people are using. I know the amateur community is staying well abreast or even ahead of what professional or facility telescopes are doing, because it's software and you don't have to have tens of millions of dollars to go build a giant telescope. And yeah, it's amazing what some of the deconvolution results I've seen from fast imaging of Jupiter, for example. You get incredible images.
Yeah, indeed.
So Mike is also pointing out that the Lowell Observatory mirror is about 4 inches thick, and it is held with actuators to improve the seeing capacity of that. What's the range of movement in the actuators in millimeters? Do you know that?
Gosh, again, I don't really know. It's going to be larger for our mirror because, like I say, it's a secondary, and so it's larger diameter. But I believe it's small because I think it's on the order of wavelengths of light. So I'm going to guess it's in the less than 10 microns from peak to valley. But that's sort of a guess.
Any other questions? On behalf of PAS, Doctor, thank you very much for your time and your information. And I am sure, as Arizona residents, and then we have some snowbirds that come and go in and out, and they will find their way thanks to you visiting us this evening with your expertise and presentation. We've learned a little bit more about deformable mirrors, angular resolution, and I had one final question. Spectroscopy, when you had mentioned it briefly, and I'm wondering, when you combine all of what you described, the deformable mirror and the angular resolution, are you then applying spectroscopy to the game and getting better results with that as well?
Yeah, there's definitely adaptive optics is benefits spectroscopy as well. For one, for example, we have a new instrument iLocator coming on, and what you can build a spectrograph which is much smaller because you have this AO corrected beam coming in. It's much smaller, and so the spectrographs can be less expensive. And then also using what's called an IFU, a slitless spectrograph. Those are quite common, where you can basically have spectral information at each spaxel. So you get both. You get the high spatial resolution, but then having spectral information at each resolution element. So yes, spectroscopy and AO are definitely used hand in hand.
Again, Dr. Al Conrad, thank you very much for your time this evening. We truly appreciate it. By the way, we recorded this lecture and we will be uploading it on the website for your fan base.
Okay, great. Thanks. Send me the link.
Okay.
All right. Thanks for your time.
All right.
Bye-bye.
And now I have to do this, if I can do this correctly. Let's see. My apologies. I did it. By golly. Okay. Couple bits of information. As a reminder, ladies and gentlemen, we have a star party scheduled for November the 16th, 6:30. And as we always say, and hope you comply, as you did for this evening, you register with our on-site website at pasaz.org. And again, the reminder, the reason is if Mother Nature causes us to have to cancel the event because of weather, we want to be able to tell you about that, like we had to do, unfortunately, for our last. But it's been rescheduled, and this is the new rescheduled date for that star party that we had to cancel last week. So hopefully you got that information. There's a telescope workshop at the community college that I mentioned to you. That's November the 21st. Operating or buying a telescope. You must pre-register for this as well. And by the way, if you how to operate your telescope, if you have an issue on want to bring in your telescope and say, I don't know how to operate this thing, it's been in the garage for months, if not years, what do I do? When you register, please get in touch with us and tell us what your telescope is so that we make sure we have somebody who's familiar with your make and model of telescope. Again, it's November the 21st on campus at 32nd Street and Union Hills, 7:30 p.m., operating or buying a telescope. If you are a first-time thinker about buying a telescope, we have a lecture for you at that same event. So write the date down and sign up. Your board of directors meets once a month, and it will be on Monday, the 18th at 7 p.m., and the public is invited. And finally, next month, Dr. David Williams, he has been with us before. This is one fantabulous. My mama told me never to use a word I can't spell, but I think I can do that one. He is one fantabulous lecture guy from Arizona State University. As many of you know, ASU and the U of A, they might compete on the field of football and in basketball and baseball, but boy, oh boy, they get together on a lot of science projects, especially with NASA, and he is one of those guys that can tell us a lot. His topic to be decided. I am not sure that we've been told what he's going to be sharing with us. Once again, December the 5th. It's always a Thursday night, 7 o'clock for us to meet and greet, and then the lecture starts at 7:30, as they say across the pond. And then my final message for all of you is that thank you for your continued support of PAS. We're always looking for suggestions, and you know how you can get in touch with us by contacting me at president@pasaz or any one of our board members. Again, clear skies, everybody, and I will close out now unless anybody else has any comments, questions that they'd like to share before we sign off. The floor is yours if you wish. I hear none. So, ladies and gentlemen, I guess it's time for me to say good night. Au revoir, adios, merci beaucoup. And as they show in sign language, this is the International Sign, American Sign Language. It means I love you. We love your support and your involvement in PAS, and hopefully we've provided you another tidbit of information